Okay, I hope I am audible to everyone and my screen is visible to all of you. So I think we'll just wait for 2 more minutes and then we'll start the session. And in the meantime, if somebody else joins, I'll keep letting them in the meeting room. But we'll start with our session. So in the last session, we saw some of the synthesis protocols, synthesis methodologies of different kind of nanoparticles, uh, carbon dots, and all those things. What are the different methods available by which we actually synthesize nanoparticles? Now, in this particular session, the whole focus, the primary focus would be to see like what are the analytical methods, what are the methodologies by which we can actually characterize that whatever nanoparticles we are formed, what are their characteristics, like if they have been formed or not, what are the different I would say characterization parameters based on which we conclude, we experimentally validate that a particular kind of nanoparticles are formed or not. So we'll just, I think, wait for 1 more minute and we'll start with the session. And as like as the people will keep on joining, I'll let them in the meeting room.
Hello, good evening, ma'am.
Good evening.
मैम मैंने आपसे पिछली क्लास में वो उसके लिए
Yes, yes,
बोला
yes.
था
I,
अनाउंसमेंट बॉक्स में ऐड करने
I'll,
के लिए।
I'll show you the mail. I'll show you the mail. I talked to them actually regarding you, and
यस मैम।
just a second. I raised this concern, so they told me that kindly ask the learner to check the spam folder. If the issue still persists, you can write mail to this support@nptl.itm.ac.in. So maybe you
ओके
can
मैम।
click a picture or take a screenshot of this, and maybe you can, if first check your spam folder, and if you cannot find the mail or the group link in that, you can simply mail here support@nptl.iitm.ac.in, and you'll get access to that.
ओके मैम, थैंक यू।
Okay, so I think we can start with the session because we have to discuss a lot of things. My I guess if at any point you guys feel that my voice is cracking or the screen is not visible, please let me know in the chat box. Okay, just a second. So, okay. So, like in the last session also, I've introduced myself. My name is Anusha Srivastava. I'm a PMRF fellow at IIT Indore, and currently I'm doing teaching assistantship under NPTL for experimental nanobiotechnology. That is course code BT50. Now, in this week's session, like the week 2 experimental nanobiotechnology course content, so this is the syllabus. I mean, this is the course content. So there are different spectroscopic analytical techniques that we'll be discussing: UV visible and fluorescence spectroscopy, dynamic light scattering and zeta potential analysis, FTIR, X-ray diffraction, electron microscopy, and atomic force microscopy. Now, if we talk about nanoparticle characterization, there could be multiple, methodologies, methods by which you can do the characterization. But these are some of the most commonly used methodologies, or we could say some of the most resorted methodologies that are used for nanoparticle characterization. Now, uh, starting off, suppose you have synthesized, like in the last session, we discussed that we synthesize nanoparticles. Now, suppose by varying the, different parameters like the concentration of the precursor, the concentration and amount of the reducing agent, temperature, pH, a lot of things, you, uh, you know, by all these variations, you synthesize nanoparticles. Now, at this point, you have these different types of nanoparticle suspension, or maybe if you have followed some different methodologies, you have lyophilized or you have calcinated the sample, so you have this powder. Now, based on this and this, we cannot experimentally, validate, or maybe we can scientifically say that we have synthesized nanoparticles, because we cannot find out if nanoparticles are successfully synthesized by just looking at the suspension or powder. Now, at this stage, we don't know if the nanoparticles have been synthesized or not. So, in order to experimentally prove what you have synthesized, there are different methodologies available, and we'll deal it one by one. So, the first one is UV visible or fluorescence spectroscopy. Just a second. So, UV visible or fluorescence spectroscopy. So, in this UV visible thing, which is basically that we call as absorption spectroscopy as well. So, in this, uh, the, this is the light source. Suppose this is the light source. So, the light passes straight through the sample, and we detect that. In case of fluorescence spectrophotometry, what happens is, like, this is the basic principle. I guess all of you would already know, like absorption, fluorescence, emission. But still, we'll just touch upon some of the very important points that needs to be revisited, and some of the the principles that governs these spectroscopic methods. In fluorescence spectroscopy, the light passes through the sample, but we detect a different wavelength. So what does it mean? Now, suppose if we are recording the absorption spectra of IgG, immunoglobulin G. Suppose if we are recording the absorption spectra of immunoglobulin G in PBS. Now we know that this is made up of it has aromatic amino acids tryptophan and tyrosine, because of which it gives absorption at 280 nanometers. Okay, so we can see the peak here. Now, if we want to know that if in a particular sample there is IgG, we'll pass the light through the sample, and then based on which components of light are absorbed, like suppose this is IgG in the sample. Now this IgG would particularly absorb at 280 nanometers. So only that light would be absorbed and the rest of it would be transmitted. So, but in case of fluorescence spectroscopy, what happens is we excite the sample with a particular wavelength of light, but the detection happens at a different wavelength. Now look at this fluorescence emission spectra. This blue line indicates excitation. Okay, so suppose we excited the sample, sorry, suppose 350 or 375 nanometers, but we record the emission wavelength. The emission wavelength is somewhere around uh, like between 450 and 500 के बीच में there is the emission wavelength. So in this case, this is different. Now this is something very basic. Now let's delve deeper into it. When we talk about UV visible versus fluorescence spectroscopy, so UV-Vis spectroscopy is an analytical technique that uses the absorption or reflectance of a part of the UV range. Suppose we are supplying light from 200 nanometers. Now to nowadays, it's not just limited to visible range like for up to 700 or 800, 750. Now you can go up to like 1200, 1400, like UV visible NIR spectroscopy is also available. That is UV visible NIR. So UV spectroscopy is an analytical technique that uses the absorption or reflectance of a part of the UV range and complete adjacent visible regions of the electromagnetic spectrum. Now, when you are passing the light, it has all the wavelengths in it. Now, from all the wavelengths, only a particular section of wavelength would be absorbed, and this particular wavelength that is being absorbed is characteristic of the sample. Like that particular sample will absorb that specific wavelength only. Then, but in case of fluorescence spectroscopy is a type of electromagnetic spectroscopy that is useful in analyzing fluorescence from a sample. Now, measures the absorption of light in the range of UV visible frequency. Nowadays, NIR is also available after absorbing light at a high energy than the emitted energy level. But this measures the light emitted by a sample in this range after absorbing light at a high energy than the emitted energy level. So the sensitivity in this case is low, but in this case the sensitivity is very high. Like at a very low concentration also, if the material, if the nanoparticle that you are analyzing, or if the quantum dot, carbon dot that you are analyzing has that particular characteristic of showing fluorescence, then even at very low concentration also you can detect the fluorescence emission from that. Now, measuring the absorption, measured with a reference beam, measured without a reference beam. Now this is a very important point. We'll see what does this mean in the next slide, where we'll discuss about the instrumentation. Now we'll go one by one. So once we finish the UV visible and fluorescence spectroscopy, all the slides related to this particular section, you will be able to relate what exactly we were talking about, how this particular process happens, and how this particular process is actually helpful in characterizing your nanoparticles. Now, in this case, the detection limit is comparatively high, and the detection limit is extremely low. The molecule absorbs a photon from a light source, which is xenon lamp or laser. The energy kicks an electron from its ground state, like the electronic transitions you all would have studied in your basic classes. So from the ground state, after absorbing energy, it kicks an electron from its stable ground state, that is S naught, to a higher energy excited state, which could be S1 or S2. Usually, wavelength is usually stored like higher energy, often in the UV or blue-green region, and the molecule stays in this state for a tiny fraction of second. Only it stays for a tiny fraction of second. Now, when we talk about emission process, because obviously if it has been, you know, went to the excited state, it will try to come back to the ground state only. Before the electron returns to the ground state, it loses a small amount of energy through internal vibrations. It then drops back to the ground state, releasing the remaining energy as a new photon of light. So the emission wavelength is always longer. That is why if you are exciting, suppose if you are exciting a molecule with wavelength 350 nanometer, you would always get emission at a higher wavelength. Why this happens? Because there's always a kind of redshift that you would observe. Because the energy gets lower. In this process, when the molecule is getting excited, going to the excited state, and then while returning back, it loses small amount of energy. So there is lowering of energy. And as we know that with this particular relation, E is equal to hc by lambda or E is equal to h nu, we know that energy and wavelength are inversely proportional. So if there is decrease in energy, obviously the wavelength would be longer. That is why you see this shift. That is why you see this shift, this red shift. So this is the light the detector usually see. Just a second, I'll let people in. Okay. So moving forward, now one thing that is extremely important, I don't know if that has been discussed or not, or if you guys are aware about it, this Jablonski diagram. So this is a very interesting concept, and it is an amalgamation of all these optical phenomena that happen at the molecular level. Like from this particular diagram, from this one single diagram, you can understand what electronic transitions happen in case of absorption, in case of fluorescence, in case of phosphorescence. What does internal conversion, intersystem crossing, and vibrational relaxation means? So this Jablonski diagram was named after this Polish physicist Alexander Jablonski, who proposed this, and it is a visual representation of the electronic states and transitions, like different electronic states as well as the transitions that happen, both radiative and non-radiative, that occur in a molecule after it absorbs light. So whenever a molecule absorbs light, whatever electronic transitions happen between different electronic states, it gives account of those all those transitions, particularly used in fluorescence spectroscopy. So as you can see, this is the ground state H naught. Now once the molecule or the sample absorbs energy, it can go either to S1 state or to S2 state. Now once if there is if the molecule is coming back to the same electronic state, like from S2 to S1, we call it as internal conversion. But if it is going from S1 to T1, we call it as intersystem crossing. And once the system absorbs light, and then if it's coming from S1 to S naught, then we observe fluorescence. We observe absorbance whenever it gets excited from ground, that is S naught state, to either, just a second. So either S1 or S2, we see absorbance. Whenever the molecule comes back to the ground state from S1 state, we observe fluorescence. Now, whenever there is this chance of intersystem crossing, whenever intersystem crossing happens and the molecule comes back to the ground state from T1 state, so whenever there is transition from T1 to ground state, that this we observe phosphorescence. So this diagram is a very interesting concept, and it gives you an account of all these electronic transitions that happen between different electronic states whenever a particular molecule or compound absorbs energy. So moving forward, we'll study this in a little brief. So I see molecular transitions between electronic states of the same multiplicity. Now spin multiplicity and this thing, I think because we don't have to discuss this, this is something 11th 12th class concept. So this splitting of energy states and all those things. You guys would have studied it. But here we are mainly focused about this like IC and intersystem crossing, internal conversion and intersystem crossing. So whenever the molecular transitions happen between electronic states of the same multiplicity, like from S2 to S1 or S1 to S0, we call it as IC. But whenever transitions between electronic states of different multiplicity, like this is S1, this is singlet oxygen state, this is triplet electronic state. So whenever it happens between electronic states of different multiplicity, like singlet to triplet, we call it as intersystem crossing. So you have to remember this. Now, the Jablonski diagram represents the electronic states of a molecule and the possible transitions between them. And what does it help? It helps in understanding various photophysical and photochemical processes. The main processes depicted in a Jablonski diagram include the first one that we studied, absorption. Like it will absorb energy, it will go to either S1 state or S2 excited state. It transitions from the ground state to an excited singlet state. This process occurs in femtoseconds, like it happens very quickly, 10 to the power minus 15 seconds. Now, after excitation, the molecule undergoes internal energy redistribution, moving to lowest vibrational level of the excited state. Okay, so that this thing that we see, vibrational relaxation in the same electronic state, undergoes internal energy redistribution. This happens in picoseconds. Now, internal conversion, this is a kind of non-radiative process where the molecules transitions between electronic states of same multiplicity. The energy is lost as heat to the surroundings, and this also takes pico to nanoseconds. And fluorescence, this one is important. Like in fluorescence, there is electronic transition from S1 state to S0 state. Now, intersystem crossing, we already discussed from S1 to like from singlet to triplet state. We observe phosphorescence phenomena whenever there is transition from triplet excited state, this triplet excited state to the ground state, that is S0. It happens in microseconds or minutes. Now, see the difference. Did you notice? Like when in case of when we are seeing absorption or for that purpose like fluorescence also, these are happening in femtoseconds or nanoseconds. But this phosphorescence, this phenomena is taking microseconds to minutes. Means it is a slow phenomena. You'll observe it slowly. It's not a quick phenomena that you will run the sample and it happens immediately. So it's a very slow process that you can observe. Now, non-radiative relaxation, excited states lose energy without emitting light, and this foster like fret and all these concepts you study later on, because this is a completely like different thing that we'll discuss when we'll start discussing about cell-based studies and all those things, the dyes that are used, how this fret phenomena can be used for different applications. Now, photochemical reactions, some excited molecules undergo permanent chemical changes leading to photooxidation, photobleaching, or bond dissociation. Now, when we are talking about specifically UV visible spectroscopy that is mentioned in your course content, so this is the range that we are dealing with from 200 nanometers to approximately like 750 to 800 nanometers. Now, this is used for detecting organic and biological molecules, works on electronic transitions, mainly pi star to n pi star. Now, these are all some basic chemistry, but let us come to our topic of interest, like some of the very basics and how these are used to study the nanoparticle characterization. Now, four important terms that you need to remember, or I guess a lot of you would already be aware of, are these. Like whenever there is shift in the wavelength, shift towards higher wavelength, we call it as red shift or bathochromic shift. Whenever there is a shift towards lower wavelength, like this x-axis, which is representing wavelength, from 0 to higher on. So whenever there is increase in wavelength, we call it as bathochromic or red shift. Whenever there is shift towards lower wavelength, we call it as hypsochromic or blue shift. And then based on that, absorption shifts to shorter wavelength due to increased polarity. We call it as hypsochromic shift or blue shift. Absorption shifts to longer wavelength due to conjugation or solvent effects. We call it as Z shift. Now, what is hyperchromic or hypochromic? Increased absorbance. Usually y-axis, whenever we are looking for absorption spectra, at y-axis we have absorbance. So whenever there is increase in absorbance intensity, we call it as hypochromic. hyperchromic, and whenever there is decrease in absorbance, we call it as hypochromic. So all these things, like whenever you are making nanoparticles, suppose you are recording spectra of a free drug. First, we'll see these examples as well. Now, suppose at first you're recording spectra, absorption spectra of a free drug, and it shows a sharp absorption peak somewhere around 300 nanometer. Now, this is for free drug. Now, when you load this in nanoparticles, there would be some kind of uh, chemistry happening, there would be some loading, capping, and some different agents. So, because of this, you would see some difference in the absorption peak of this molecule and the drug that has been encapsulated in this particular nanoparticle. There could be some kind of shifts or spectral broadening, or you can see the spectra somewhere like this. There could be, it could be like this, or it could be like this as well. Some spectral broadening or a minute shift, like not a lot of it, but minute shift, like 5-10 nanometer kind of thing. So, based on these difference in the absorption spectra, we kind of interpret that the difference between our free drug and the nanoparticle. Now, the basic principle of absorption spectroscopy, we all know about Beer-Lambert's law. When a beam of light is passed through a transparent cell containing solution of an absorbing substance, reduction in intensity of light may occur. So obviously, this is the source. It passed through monochromator, which would allow a particular wavelength of light to be incident on this cell or cuvette, and this would be the transmitted light. So based on what transmitted light is detected by the detector, then this particular like formula, or I would say the correlation, we apply to calculate the absorbance. So higher concentration means higher absorbance, longer path length, higher absorbance, higher molar absorptivity, higher sensitivity based on this formula. But this one is important in this slide. Like, what is the limitation of Beer-Lambert's law? The limitation is the Beer-Lambert law provides a linear relationship between absorbance and concentration, but is limited to dilute solutions. Like, this Beer-Lambert law is limited to dilute solution of less than 0.01 molar. And when we are using monochromatic light, like having single wavelength, and when we are dealing with homogeneous samples, this particular law fails at high concentration due to electrostatic interaction and refractive index changes, and requires non-scattering, non-fluorescent samples. This is the star point, I would say. Always remember the limitation of all the law, all the methodologies that we are studying. Now, this is the incident light, transmitted light. This is the like based on the transmittance that is detected by the detector, that is being correlated to work out this absorbance formula, I would say, to calculate the absorbance. Now, these are some of the important, like these are the absorption spectra of different chlorophyll molecules, like chlorophyll A absorbs at what wavelength, chlorophyll B, and all this. Now, come to the instrumentation part. Now, from here, we'll start more into the application based purposes. Just a second. I hope my screen is visible and I'm audible. Okay. Okay. So this is the instrumentation. Now, if you remember, we were talking about from 200 to 800 nanometer, right? We are dealing in this particular range. So from 200 nanometer to 800 nanometer. Now, in this case, if you see, there are two sections of electromagnetic spectrum, UV and visible. So for both kind of, I would say, the spectrum that we are working with, there are two lamps employed in this particular UV-Vis spectrophotometric machine. Deuterium lamp, which works in this UV range, tungsten halogen lamp, visible range from 200 to 400, 400 to 800. So there are dual light source in this UV-Vis spectrophotometer. So dual lamps, dual light sources are housed. Now, monochromator, what is the function of monochromator? It selects a specific wavelength of light, prism, diffraction grating. Then there is a sample holder. Now, be mindful, just look at this. Now, there are two different sample holders. One is for the reference, and the other is the sample that we are analyzing. Now, this is the reference At this position, you put the reference cuvette, and this is your experimental sample. Now, whatever readings, whatever absorption or spectra that you will record, it will be in reference to this one. Now, in reference, what we put, suppose you have your nanoparticles suspended in DI water. Okay, you have your nanoparticles in DI water. So this is your experimental sample. So in the reference, what you'll put in the cuvette? In the cuvette, you will simply put the DI water in this reference cuvette. If you have dissolved or you have resuspended your nanoparticles in some other solvent like PBS or any other solvent, you would put PBS in the reference. So this is very important. So whenever we are recording the absorption spectra, you need to put a reference uh, sample in the separate cuvette. So for UV measurements, glass cuvette; for visible region measurement. So if you are like measuring in UV, you can use quartz cuvette, or if you are only doing for visible region, you can use glass cuvette. And then always remember the name: photomultiplier tube and charge coupled device detector, which are used for the detection. Now this is the instrumentation for fluorimeter. Now, there are some very key differences that you'll find in the instrumentation setup and this sample chamber as well in case of when we are recording absorption and when we are recording fluorescence. In this case, using fluorimeter, this device, we are recording the fluorescence emission given by a particular kind of sample. So, in this case, like if you remember here, the light is passing straight, okay? But here there is a 90-degree, you would see a 90-degree angle here. So suppose if the light is coming like this is the apparatus, this is the lid. When you will remove the lid, you will see something like that. So if you will remove the lid, you will put like remove it. So the inside of the instrument looks like this. Okay. So this is the sample chamber. As now one difference that you guys would have noticed here is in case of absorption spectroscopy, there were two cuvettes. There were like space for two cuvettes. We were putting two different cuvettes. Now in this case, you can simply put one cuvette. So the light will come and it will go at 90 degrees angle, the 90-degree angle that you will observe. So this is the difference. You don't have to take a reference sample for it. You can simply put your sample here. Now, this is one thing. A fluorimeter is an instrument used to measure the intensity of fluorescent light emitted by a sample after excitation by a specific wavelength. So, you will do the excitation. So, the light will come somewhere from like this. It will fall on the sample and then at 90-degree. It will be deflected 90-degree. Just a second. It will be deflected 90-degree. Now, instrumentation, when we talk about instrumentation, simply there would be a light source, provide excitation light, and the common sources are xenon lamp, mercury lamp, LED, or laser. Excitation, monochromator or filter. What does, we all know what is the use of monochromator? It selects a specific wavelength to excite the sample, and that specific wavelength is chosen by us. Like we'll write in the dialog box that with which wavelength we want to excite our sample. Sorry. Now the sample holder, which is usually made of quartz cuvette, it is positioned so emitted light is detected at 90-degree to reduce interference from transmitted light. Now this is a star point. Always remember that why, if somebody asks you why in case of absorption spectroscopy the light is passing straight through the sample and we are detecting the transmitted light, and then we are correlating this transmitted, whatever transmitted light is being absorbed, with the absorbed light. But in case of fluorescence, when we are recording fluorescence or when we are doing this fluorimetry, why do we, why there is 90-degree deflection? So the answer is it is positioned at 90 degrees so that the emitted light is detected at 90 degree to reduce interference from the transmitted light, because there would be too much interference from the transmitted light as well. Now, emission monochromator or filter, which again select the emitted fluorescence wavelength. detector which converts emitted light into electrical signal, and again the detector is same photomultiplier tube. Now there are some other highlights and other points as well. You need to take care of the fluorescence intensity. Just like in absorbance we saw, in fluorescence spectra also, this y-axis represents the fluorescence intensity, okay, and this x-axis represents the wavelength. Now, when you are recording the spectra, whenever you are recording the spectra of any sample, you need to take into account that the fluorescence intensity is not too high, maybe not above 1 lakh or something, because if the fluorescence intensity is too high, will be too high, it will damage the PMT. And once your PMT is damaged, you will not be able, like, obviously the machine would come to end. So there is a safe limit, like it is mostly mentioned in the manual as well, that always see, always take care of that the fluorescence intensity is not too high, because it would damage your PMT. It would damage your PMT. Signal processor and readouts amplifiers, these are common. So now we have seen so far we have seen the instrumentation for UV visible spectrophotometer. We have seen the key differences between UV-Vis spectrophotometer and the fluorimeter that we use to record fluorescence emission. Now, let's understand absorption spectra of different molecules. Now, if you remember, in the previous class also, we also discussed about different type of gold nanoparticles that are available, like spherical, rod shaped, and then there are some like other shapes as well, like gold stars, gold urchins, and all those things. Now, suppose you have, suppose this is the gold nanoparticle suspension. Okay. Now, at this stage, when you have this, you don't know like what is the size of the nanoparticles present in this suspension. But when you will record the absorption spectra, when you will record the absorption spectra of this particular sample, you'll you'll see either of one of these wavelengths. Suppose you observe a wavelength at somewhere around this, somewhere around 520, 520 or less than 520 nanometer. You took this sample, you put it in a cuvette, and you put this cuvette in an UV visible absorption spectrophotometer and recorded the absorption. You found a wavelength like somewhere somewhat like this, okay, at 520 nanometer. Now, based on this, what you can say, because this is available in literature, you can say that the nanoparticles that are formed, nanoparticles that are present in this nanoparticle suspension are of 20 nanometer size. Like, this is a kind of preliminary analysis. Now we'll also see, because whenever we are talking about nanoparticle characterization, it's not like you have synthesized this and now you did the absorption spectroscopy, you got like, yes, okay, so you have a absorption peak at 520 nanometer and then the work is completed. You have to experimentally validate with other techniques also, and all those techniques shall correlate with each other in order to uh, you know conclusively say that whatever nanoparticles you are proposing, that we are synthesizing gold nanoparticles, these are spherical in shape, the size is 20, the diameter is 20 nanometer. So in order to say that conclusively, you need to corroborate each of the different findings with each other. Now we'll see one by one how that happens. So suppose you say, like, you got 520 nanometer absorption wavelength, and based on that you say that okay, that my nanoparticles, we can preliminary say that the nanoparticles are in this range. Now this data is from one of my recently published papers. So suppose this is a free ICG. Okay, so this indocyanine green, basically it's a fluorophore. It's an FDA approved dye that is used for imaging. So as you can see, there are two different absorption peaks, maxima that we can observe. So the primary peak is around this 780 nanometers, and a shoulder peak at somewhere around 710, 720. Now, when we load this free ICG, this free fluorophore, in a nanoparticle, okay, just a second. when we load this free ICG, which is green in color, in a nanoparticle and then observe the spectra, we'll see that there is spectral broadening happening, which is also an indication of the formation of nanoparticles. So if we want to see, like, okay, this is the the free compound, and when we are loading it in a nanoparticle, there's also a slight change in the color and also spectral broadening that we are observing. So based on these features, we can also preliminarily say that, okay, my nanoparticles are kind of formed. Now moving forward, for the same thing, like when we see the emission spectra, this is also from that paper only. So this is the free fluorophore, free ICG, which shows emission at 800 nanometer. Now the absorption of this particular compound was at 780, but the emission is at 800. So that's what we were discussing in the initial slides, that the emission wavelength is always, a little redshifted. Now, when we'll see the emission spectra, in emission spectra, we'll also see there is a kind of little spectral broadening that we are observing when we are loading this free ICG in nanoparticles. So these are some of the indications that are studied while, synthesizing nanoparticles and comparing free compound with the loaded one. Now, coming to electron microscopy. Now, suppose at the first stage, what we did, we have seen like we are getting a particular spectra, and now we know that if we are getting a particular wavelength of light, that is characteristic to a particular kind of nanoparticle that we are talking about. But still, at this level also, we have not seen if the this wavelength is because of these spherical gold nanoparticles. Now we need to visualize it. So for that, because we are working in nanometers range, okay, so since we are working in nanometer range, we cannot use microscope, we cannot see via, like, the simple optical microscope that we have in the lab. So electron microscopy works exactly like optical microscope, except, and what is that exception? They use a focused beam of electrons instead of light to image specimen and gain information as to its structure and composition. Electron beam is only capable of penetrating around 100 nanometers, means it is, and like it works, this electron microscopy works in the nanometer range to obtain high quality image and optimized resolution. So this is the like the basic, very, I would say, the layman language for explaining what exactly is electron microscopy. Now, there are two different techniques which are mostly used when we talk about electron microscopy, and the first one is scanning electron microscopy, right? Now, what happens in scanning electron microscopy? So, this is your sample, okay? This is the stage, and then you put your sample here. Now, this sample could be, suppose you have a, like, if you have a nanoparticle suspension that is in aqueous state, what you need to do is you need to take a small glass slide. You need to cut this glass slide using a diamond cutter and drop, drop that nanoparticle suspension and let it dry in a desiccator. Dry. It should be dry. Whatever sample you are putting for scanning electron microscopy, whatever sample you are putting in your scanning electron microscopy, it should be well dried in a desiccator. There should be no moisture. So that is very basic. You dry it, or if you have a powdered sample, what you can do is simply take a glass slide and in both the cases put carbon tape on it. Now carbon tape is used, this carbon tape is used basically to increase the conductivity. So whatever sample you will put, either the glass slide or anything, that needs to be put on the carbon tape. Now there would be carbon tape. On the carbon tape, put your glass, like directly, like this is the carbon tape. Put your powdered sample on this carbon tape and then put it on the this sample stage stuff. We'll see that. Now you put your sample here. There is a very fine energetic electron beam that would fall on the sample, and it will lead to ejection of secondary electrons and backscattered electrons. Now these secondary electrons and backscattered electrons are used together to create a 3D image of your nanoparticles. Now, how this happens? Again, this is the same thing. Like this is the electron gun, electron beam. Then this is the condenser lens, which is basically to uh, focus this electron beam more. Then it passes through the objective and falls on the sample stage. Now, the backscattered or secondary electrons that are rejected, these is like taken up by the secondary electron detector, and this 3D kind of image is made. So in SEM, scanning electron microscopy, a focused electron beam is scanned across the surface of a sample in a vacuum. The interaction between the electrons and the sample, so whatever interaction happens between these electrons and the falling electrons and the sample, generate secondary or backscattered electrons which are detected to produce high resolution images of the surface morphology and topography. Now, this is the instrumentation. Whenever you go to labs or you'll see you'll see a system like this. So this is scanning electron microscopy. Now, if you see here, there is a door handle here. Okay, this is a handle. When you'll open this door, you'll see a sample stage is there. So at that sample stage, this is the kind of sample stage that is there. So these holes that you see and these rounded stages that you see, we call it as stubs. These are called as stubs. So you can put, like, in most of the cases there you can maximum put 9 of these stubs on these, like, and on these stubs you put the carbon tape, and after putting the carbon tape you can put your powdered sample. If there are powdered sample, you can put a little amount of powdered sample on this, and this whole thing is put inside. When you'll open the door, there is a stage, you put this here. Now you'll close the door and you'll make vacuum. You'll give command for creation of vacuum, because this electron microscopy, this scanning electron microscopy, like this detection happens in the vacuum environment. So sample stage with steps, sample on carbon tape. Now, why do this particular system use secondary electrons and backscattered electrons? Secondary electrons are used to provide high resolution surface topography, and backscattered electrons reveal compositional contrast based on atomic number. So the heavier elements will appear brighter. So there would be a kind of contrast that you will see. Okay. So a scanning electron microscope generates high energy electrons from a gun, accelerating them down a vacuum column. So it comes down through a vacuum column where electromagnetic lenses focus them into a fine beam. This beam rasters across the sample. Now, this is an important term, okay? What does raster scanning mean? Like, kind of like this. It will scan your sample like this in a nanometer range. Like, there would be a dot kind of, suppose this is the size of the sample, and this would be how the scanning would happen at this nanometer range. So it rasters. This is the kind of raster scanning, okay, when it moves like this across the sample surface, causing the emission of secondary and backscattered electrons, which are detected to create high resolution 3D images. Now, how this happens? So you will see something like this. If you clearly see, this is some three-dimensional kind of images that you are observing. You can see the topography, and at some positions there is a kind of gradient of black and gray that you would observe at some positions it's like quite bright, a little darker. So there is a kind of gradient that forms. So this is a 3D reconstruction kind of thing. Now, we also studied that gold nanomaterials can be synthesized in different shapes, like nanospheres, nanorods, nanoparticle, nanocluster, nanoflowers as well, nanowires as well. Now, if you remember in the previous session, I told that in the subsequent session, we'll also see that why these kind of structures, these nanoflowers, or maybe these nanostars are important, and in which application these are used. So these pointed surfaces, these shapes basically act as hotspots for the electromagnetic radiation that are falling on it, and basically, like I'll show like why is it important. At this point, you can see like these images, these rods and all those things. So there's a kind of like 3D structure that we can see with scanning electron microscopy. Now let us see what these differently shaped nanomaterials are used for. Now, the shape primarily dictates the localized surface plasmon resonance, which determines which wavelength of the light particle absorbs and scatters. Now, all these, there would be difference in the absorption spectra of all these gold nanomaterials. It will show somewhere around 520 nanometer. Now, these nanorods show two different peaks. You would see two peaks, one transverse peak and one longitudinal peak at like this would be somewhere around 5 10 15, and this would be somewhere around 1050 or 800 kind of thing. So you will observe two different peaks for this nanorods, same different absorption peak for nanostar as well. So nanospheres absorb in the visible region 520 to 540 nanometer, and these looks red in solution. Nanorods have two LSPR bands. I showed you two different localized surface plasmon resonance band. By changing their aspect ratio length to width, they can be tuned to absorb NIR light, which penetrates deeper into human tissue. Now, one thing is these cold nanorods can be tuned. Like you can synthesize a rod like this, but by tuning the property, you can also synthesize a rod like this. Now, these ones with longer aspect ratio, they can absorb light in NIR region as well. So you can modulate the absorption wavelength as well by carefully tuning the optical properties of these gold nanomaterials. Now, nanostars and urchins feature sharp tips. If you see this, these are sharp tips. Now, what is the function of these sharp tips? They act as hot spots, dramatically amplifying electromagnetic fields. So, whenever electromagnetic will fall here, so whenever the electromagnetic field would fall here, especially in case of Raman spectroscopy, I'll just very briefly explain. So this Raman spectroscopy or this Raman phenomena, when it was discovered, so the thing is only 1 in a million molecule gives Raman scattering, shows Raman scattering. So since only 1 in a million molecule shows Raman scattering, what happens is the Raman spectroscopy signal is very weak. Now, then this surface enhanced Raman spectroscopy, what happens in this? Suppose we have an analyte and we couple it with this molecule like some gold nanomaterial. So when we combine our analyte with these gold nanomaterials, which shows surface enhanced Raman spectroscopy, what would happen is we'll get a very sharp and fine Raman signal. So this improves the detection, I would say, efficiency or detection limit, or it improves the signal to noise ratio. The correct term would be the signal to noise ratio will get improved by combining the analyte with the nanomaterials, which shows this LSPR property. So if we'll combine our analyte, or if there is this, you know, a substrate on which we have coated it with nanostars, and then we put our analyte on it. So in this case, the electromagnetic radiation will fall on it. There would be increase in the resonance and increase in electromagnetic field, and whatever Raman signal that we'll detect, the signal to noise ratio of that signal will be very good. So that this is called a surface enhanced Raman spectroscopy. So this makes them ideal for surface enhanced Raman spectroscopy to detect single molecules. So this is how these are used. Anybody writing anything? Now, moving forward, coming to transmission electron microscopy. What is transmission electron microscopy, and how this transmission electron microscopy is different from scanning electron microscopy? Sorry, I cannot see if like the session is going on. Just a second. Okay. So how this is different from scanning electron microscopy? So transmission electron microscopy uses a high energy electron beam that passes through an ultra thin sample. Transmitted and scattered electrons are then focused by electromagnetic lenses to form images that reveal the internal ultrastructure of the material at nanometer to sub-angstrom resolution. Okay, now see the difference. So this image is of a pollen grain that has been visualized under scanning electron microscopy and by transmission electron microscopy. So at this point, you can see the 3D kind of image and the surface topography, but not the internal structure and all those things. But this one, the transmission electron microscopy of a pollen grain, you can see the surface topography as well as somewhat internal structure, and there is no 3D image that you can see in this. So this is the main difference. In scanning electron microscopy, what kind of electrons are used to construct this 3D kind of image? The scattered, backscattered or secondary electrons. In this case, we use transmitted electron beam. We'll see why. Image formation, image is produced after microscope collects and counts the secondary electron. Internal or beyond electron that directly pass through the sample are the ones illuminated in the image. Focus of a surface of analysis, surface of sample, fine hairs, eye of a housefly, head of a pin. So we can see those 3D structures as well. Now, internal or beyond surface, viruses, organelles, atoms, macromolecules. So this gives a 3D kind of projection, 3D images. This is a 2D. As you can see here as well, like this is 3D and this is 2D. Do remember this difference. Special sample preparation. Sample must be stained by element that captures secondary electron. Now this one is very important. So what does this stained means? Suppose you are making a polymeric nanoparticle. Suppose your polymeric nanoparticle is made up of maybe sodium alginate or chitosan or any of the like polymer or any protein based polymer. Now those nanoparticles will not have the ability to conduct electrons. So when the electron beam will fall on it, it will not conduct electrons. So for this, what you do is, suppose this is your sample, this is your glass slide on which you have your sample drop casted on it. Okay. Now the next step, before putting this sample into the instrument, what you do is you sputter coat it. Like there is a sputter coater. Okay, what you do is you put this glass slide with your sample in that sputter coater, and that sputter coater will coat gold on it. Now it differs. Some at some places, any of the conducting material is coated. It could be gold. Some at some places like the sputter coater, they use copper as well, or any of the conducting material is coated on it, on this sample. And once this coating is completed, then you will put it in the instrument. Then you will put it in the instrument. So you need to do that. But in case of transmission electron microscopy, sample must be cut extremely thin. Actually, you don't need to, if you are talking about nanoparticles, you don't have to do it because you get TEM grids. There are very like small size TEM grids available. You simply put your sample in it. It will be strained. You dry it, and then you can simply visualize it. Now, special sample preparation, sample must be stained by element that captures secondary electrons. Sample must be cut extremely thin. Same thing. Now, moving forward, the imaging principles in transmission and scanning electron microscopy. Now, see the difference. When we were talking about scanning electron microscopy, we saw the electron gun, which is common to both. Then condenser lens. What does this condenser lens do? This is basically used to, further collimate the electron beam that is falling on the sample. So, in order to further concentrate the electron beam that is falling on the sample. Now, now, from this point, just see the difference between these two techniques. In transmission electron microscopy, after passing through the objective lens and the projector lens, this is your sample. It is passing straight through the sample. That's what was written in the previous slide. that the electron beam will straight away pass to the sample, and whatever transmitted beam would be there, and they like a mirror image kind of thing would be, you can see, and this is a 2D thing. Now in scanning electron microscopy, you'll see they detect backscattered electrons and secondary electrons, which is used to make a 3D kind of image. So this is the difference between scanning electron microscopy and transmission electron microscopy, and the very principle on which they work. Now this is the machine for transmission electron microscopy. You can see this is a straight line kind of thing. So TEM captures the forward transmitted electrons to the sample. Forwarded transmitted electrons, whatever electrons were forwarded, uh, uh, transmitted through this sample. Whereas scanning electron microscopy scans the sample with a narrow beam probe and captures various signals with different energies, including the backscattered and secondary electrons. So this is the core difference between both these electron microscopy techniques. All right. Now these are the same images. This is the same image. Now compare these two images. Compare these two images. You can clearly see like this is a 2D image, this is a 3D image, this is how it looks. Now, one important thing is if you look at these nanoparticles, like the scanning electron microscopic analysis of these nanoparticles, maybe you cannot like clearly predict that most of the nanoparticles are exact diameter because this is in 3D. But here you can simply see na, the dimensions. You can simply get a more accurate, or I would say the better resolution of these dimensions. You can see, right? With how it looks, what is the shape, like in 2D. So both these techniques have their pros and cons. Okay. So whenever you are kind of publishing a paper or proposing that you have made certain kind of nanoparticles, in order to make it more impactful, in order to make your data more impactful, what you can do both the analysis, both scan electron microscopy and transmission electron microscopy, to better prove, to better validate your data. Now, let us understand this very simple basic concept. So, whenever the particle size is less than 1 nanometer, we call it as a solution. Whenever the particle size is greater than 1 micrometer, we call it as suspension. And whenever the particle size in an aqueous sample is between 1 nanometer to 1 micrometer, we call it as colloids. Now, do remember this size range. This is how it looks. Now, whenever a colloidal particle is dispersed in liquid, like whenever like particles which have size range in between 1 nanometer to 1 micrometer, they are put in any of the aqueous solvents, what happens? Let us understand that. Its surface usually acquires a charge. Whenever you will put these particles in aqueous sample, they will acquire charge by ionization or adsorption of ions which are present maybe in this aqueous phase. So it acquires charge. Whenever a colloidal particle is put in an aqueous sample, it will acquire some sort of charge. Either it can acquire negative charge or maybe positive charge and like that. This to balance this charge, oppositely charged ions from the liquid accumulate near the particle surface. Suppose if it acquired negative charge, then what would happen? The positively charged ions from the liquid would come and it would sort of form a kind of electrical double layer. I'm explaining in very simple language, in very simple terms, because the next technique that I'll be explaining for the nanoparticle characterization relies on this particular principle, relies on this particular concept. So this forms the electrical double layer consisting of stern layer, the inner layer, which is this that we are calling as a stern layer, tightly wound counter ions directly attached to the particle surface, and the outer one. This outer one is called as the diffuse layer. Loosely wound counter ions mixed with some coions, gradually decreasing in concentration with distance. So this is the kind of phenomena that you'll notice in this particular case. Now, let us understand this. So suppose this is your particle and it acquired a particular charge when we kept it in the aqueous phase. This is the diffuse layer, like this is the stern layer, and all of this, like from here to here, it constitutes the diffuse layer. and both the stern layer and the diffuse layer constitutes the electrical double layer. Okay, so colloidal stability means whether particles in a dispersion stay uniformly distributed or aggregate. Now this is very important. If you guys remember in the earlier session, in the previous session, we talked about a term that we called as aggregation of nanoparticles. So if you are, in order to prevent aggregation, we also discussed that whenever we are synthesizing nanoparticles, we are putting some of the capping agents so that the repulsive forces are maintained and the particles do not come, so that there are enough repulsive forces and the particles do not come together and clump with each other. So this is very important. So whenever we're talking, like if we have synthesized nanoparticles, it should be stable. Where, what I mean by stable is, suppose if you are like making a colloidal, whenever you are dissolving your nanoparticle in aqueous phase in water, suppose simply you are putting in DI or PBS. So whenever you are putting nanoparticles in it, it should stay like this, okay, like this, because over the time, if your nanoparticles are not stable, what would happen? It would come together and clump like this, okay? It would clump. So it is very important that these particles are monodispersed, they are not clumping together, they are not aggregating. So that is why colloidal stability is extremely important for nanoparticles, and it means whether particles in a dispersion, whenever you are putting it in aqueous phase, it stays uniformly distributed like this. As you can see in this image, the particles are uniformly distributed, but here you can see that they are clumping together, uniformly distributed or aggregate. So controlled by the balance between repulsive electrostatic forces, attractive van der Waals forces tend to pull particles together. And there are repulsive electric forces. So what do we want? हमें क्या चाहिए? We want कि there should be enough repulsive forces between these particles. There should be enough enough repulsive forces between these particles, because if there would be enough repulsive forces, they will not come together and clump. So attractive van der Waals forces tend to pull particles together. It should be less. So the general guideline is, if the zeta potential value is greater than 30 millivolt, it indicates the stability is good, means strong repulsion or stable colloid. And if it is less than 20 millivolt, it denotes poor stability and there could be aggregation. Now, this value is subjective to what kind of sample you are making, because whenever we're talking about biological samples, or whenever we're talking about nanoparticles that are intended for biomedical applications, like nanoparticles for drug delivery, nanoparticles for theranostics. So in that case, very high zeta potential value is also harmful. It can kill cells. It is cytotoxic. So there is a soft range, like somewhere like more than 15 millivolt, but less than 25 millivolt or 20 millivolt kind of thing. It is also considered to have good colloidal stability. So zeta potential measurements are taken at slipping plane. Always remember that whenever we take zeta potential measurement, we'll see slipping plane reflects the effective charge of a particle experienced in motion, not the full surface charge. So you can see the zeta potential measurements that we record, it is at the this slipping plane. And you can see in this image, this is a stable suspension. You can see all nanoparticles are uniformly dispersed. But in this case, you can see like early stages, it would start aggregate, and over the time, it would become more aggregated and eventually clump together. So for whenever you are synthesizing nanoparticles, you should ensure that it has excellent colloidal stability as well. What is meant by colloidal stability means it is not coming together, it is not aggregating. So it's very important. Now, how do we determine this colloidal stability? By this analysis that we call as dynamic light scattering analysis, or short form DLS. So in dynamic light scattering, a suspension of nanoparticle is illuminated with a laser. Okay, this is the sample cell. You'll put your sample here and then you'll excite the sample with laser. and the particles undergo random Brownian motion, causing fluctuations in the intensity of scattered light. Obviously, if the particles would undergo, because of this energy coming from laser, which will fall on these particles, they would, come into the Brownian motion. They would interact with each other, and they would be, the scattered light that will be coming out will have different intensity. So these fluctuations are analyzed. Whatever fluctuations are happening here are analyzed to calculate the diffusion coefficient of the particle, and then with these correlation, this has been then correlated to their hydrodynamic diameter. So what is hydrodynamic diameter? Suppose this is your particle, okay, and based on the electron microscopy you figure out that this is the diameter. Now hydrodynamic diameter क्या होता है? Whenever you'll put this nanoparticle in dispersion, like in suppose in DI, there would be a layer, the electrical double layer that we were discussing will be formed. And now there would be a slight increase in their diameter. So this one is the hydrodynamic diameter. Okay, I hope it's clear to all of you. So the result provides information on the average particle size and the polydispersity index, indicating whether the system is monodisperse or polydisperse. We'll see it with the help of a data. So big particles usually result in this kind of spectra and small particles like this. So this is also from one of my paper that was recently published like last year. So we can see like this image. This is I have like kind of correlated the scanning electron microscopy image with the DLS analysis. As you can see, this is a broad range. Okay, like the particles, these are not colloidal stable, these are not monodispersed, because you can see particles ranging from like 200 to 800 to 900 nanometers. That is why you see all these aggregation here, so much of aggregation. But when we change the solvent, it improved a little bit, like 100 to 600. The range, you know, kind of decreased. But when we changed the solvent and made dissolved it in PBS, our nanoparticles, we found that the best colloidal stability was achieved in case of PBS. This is a small range in comparison to these two, right? And in addition to this, you can also see in this particular image as well, like this is so much aggregated, this is comparatively a little less aggregated than this one, but this one shows monodisperse particles. What does monodisperse means? It means the particles or molecules in a system are nearly the same size and shape. As you can see, narrow size distribution. We also saw the narrow size distribution for the hydrodynamic diameter as well, and as well as the electron microscopy diameter as well. So that's what I was explaining. What does polydisperse mean? This one is polydisperse. This one is polydisperse. Means the system has particles of many different size and shape and broad size distribution. As we can see, it's all clumped, and then here also small, big, medium. So there is a broad size range as well. So that's what I was explaining. Now, I hope it's clear up till this point. Just a second. If anyone has any question, I'll just uh, escape and check the chat box. If at any point you guys feel like, okay, fine. Now moving forward, the next technique that we have to discuss is atomic force microscopy. Now, so far, what all techniques we have already discussed? We have already discussed absorption and fluorescence spectroscopy, in which we were getting spectra. I guess next what we discussed electron microscopy. Okay. In electron microscopy, we kind of visualized what kind of nanoparticles were formed, and based on these spectra, we kind of studied the characteristic spectra that particular kind of nanoparticles or compounds will yield. Now, the next technique is atomic force microscopy. Then what happens in this atomic force microscopy? This is the setup. This is the laser. This is the piezoelectric forces trigger cantilever oscillation. This is the small cantilever that moves through the surface. Okay, this is your sample. So this cantilever moves through the sample, and based on this movement, whatever bending of light it causes, laser is coming now. When it will move, there would be somewhat bending, and whatever signals are then transferred to this photodiode. This is a four quadrant photodiode, and whichever quadrant it is falling, based on this, it also makes a 3D kind of representation. So let us study. AFM is a high resolution microscopic technique used to study surface topography, properties, and interactions. Okay. AFM works by measuring the interaction forces between a sharp probe tip and the sample surface. The probe is mounted on a flexible cantilever. Now, this cantilever, it is flexible in nature, means when it will move, whenever based, suppose it's moving like this. So this is flexible. So when it is flexible, suppose there is a rough surface. Suppose this is a nanoparticle. Now, when this cantilever will move, it will be like this, and then it will deflect a little, and then it will move like that. So, when it will deflect at this point, what would happen? This cantilever will also bend, and there will also be bending of the laser light that is falling on this cantilever. So, as the tip scans, just a second. So, as the tip scans across the surface, attractive or repulsive forces cause the cantilever to bend or deflect. So these forces cause the cantilever to bend or deflect. A laser beam is focused on the back of the cantilever and reflected into a position sensitive photodiode detector. This one. This is a four quadrant. This is called as a four quadrant photodiode detector. So whenever there would be a bending, there would be bending of this laser light as well. The deflection of the cantilever is recorded and converted into a 3D surface image. So this is the basic principle. Now there is one term mentioned here, piezoelectric scanner, and piezoelectric forces trigger cantilever oscillation. Now what does this piezoelectric thing means? So piezoelectricity and atomic force microscopy are connected in two primary ways. AFM uses piezoelectric materials like PZT ceramics in its scanners to move the probe or sample. By applying voltage, what are these piezoelectric materials? These materials expand or contract with sub-nanometer precision, enabling 3D imaging. So that is why a motion scanner is used. Then measurement in a mode called piezo response force microscopy, the FM tip applies an AC voltage to the sample. If the sample is piezoelectric, it physically vibrates, and the AFM senses this tiny movement to map the material's internal electrical domains. So the basic concept still remains the same. And suppose this is laser, it is falling on the cantilever. Now, whenever there would be a deflection, suppose this cantilever would scan, and when it will go down, again there would be bending of light. Then when it will come at this point, again there would be bending of light, because this will keep on moving. Okay. Then the quadrant photodiode tracks the position of laser beam reflected off the cantilever. So whatever light is reflected off the cantilever, it is being recorded by this four quadrant quad photodiode. So it detects vertical laser shifts to map the height of surface features. It detects horizontal laser shifts. So it detects horizontal laser shifts as well as vertical laser shifts as well. It provides the signal used to adjust the scanner height, ensuring the tip doesn't crash or lose contact. Okay, so based on this, again, a 3D kind of image is created. Now, there are different modes of atomic force microscopy. I think it's not very necessary to look into this, but still you can just have a look, like contact mode, non-contact mode, and tapping mode. Most of the time we use tapping mode only. So a tiny bend of the cantilever at the base results in large movement of the laser spot. So even if it is in the nanometer range, even if the bend is very small, like very small. Then also there is a huge bending of the laser light. Like if it is falling here, if it will bend, maybe it can come here. So the deflection, even for a very small area, the deflection is too much. So in a large movement of the laser spot by the time it reaches the detector, this allows the atomic force microscopy to detect movements as small as 0.1 nanometers. No, the range. So what are the applications? One of the application is surface morphology at nanoscale. Like we were also seeing morphology and surface topography in case of SEM as well. So we can see the surface morphology at nanoscale, metal, semiconductor, polymers, biomolecules. Measuring mechanical properties, we can also look for the stiffness, adhesion, and elasticity. And biological samples like DNA, protein, cells without special coating. We do not need, like in scanning electron microscopy, if you remember, we had to coat these biological samples with gold or any conducting material because it was necessary for the electron beam to pass through it. But here we don't need to, these biological samples do not need to be coated like with any conducting material. It can simply be used without any special coating. So this is a star point. In under what conditions for or for what samples AFM is better than SEM? Like any one reason why AFM is better than SEM. So you can say this one. Now this is the atomic force microscopy of gold nanoparticles. Okay, so gold nanoparticles are casted on a glass slide, and see, this is a one micrometer scale, or maybe like that it's showing, and this is basically showing uh, like this one. This is basically showing the height. So the black regions denote like 0 or 1 nanometer of height, but this one, like if you consider this particular particle or this one, so it shows like this lightest color, so it shows like the height. If this is the nanoparticle, then this height is somewhere around 23.2 nanometer. Okay, and this scale is from 0 micron to 0.1 micron. So this is the size in 2D, and this is the size in like the z-axis. Okay, now this is also one of the AFM data. Now you can find all these in all these kind of data in literature for gold nanoparticles and for other nanoparticles as well. So that's what it denotes. Like this one denotes height somewhere around 6 nanometers based on that, and then this one also can be estimated based on different x and z axis. This one is for 8.4 nanometers. So this is how sample representation is done. This is what this kind of data is generated by the instrument. Now, comparing both all these techniques that we have studied so far, scanning electron microscopy, transmission electron microscopy, dynamic light scattering, and atomic force microscopy. So nanoparticle properties are critically dependent on the dimension of the nanoparticle, and the characterization of these dimensions is of equal importance. In this newsletter from like the source from where I have taken this section, because uh, we summarize a publication comparing three different commonly used for the dimension of nanoparticles. Three methods include these. Now see the differences. The resolution or detection limit. Whenever we are, suppose, just a second, just give me 1 minute. Okay, sorry. So in transmission electron microscopy, the resolution or detection limit is zero point 0.1 nanometer. In SEM, it is 1 nanometer. Means when we are talking about resolution, the resolution of transmission electron microscopy is better than scanning electron microscopy, right? When we're talking about atomic force microscopy, 1 nanometer XY and zero point 0.1 nanometer in Z plane. DLS 3 nanometer. So scattering of electrons, emission of electrons, physical interaction with sample, light scattering fluctuation, all these we have studied. Now, one important thing for AFM is in case of TEM and SEM, this needs to be processed and imaged in vacuum environment. But atomic force microscopy can work in vacuum, air, and liquid in all three environment, equal for all materials, size and shape. And DLS, it depends on refractive index क्या है, and usually yes, dynamic light scattering, because we see colloidal stability and all those things, so it happens in dispersion uh, environment only, like in liquid form, in aqueous state. DLS measurements are always taken in liquid state only. Now, this is something like whenever you start working on nanoparticles, you will notice that the electron microscopy diameter is always smaller than the hydrodynamic diameter that you see via DLS. So dynamic light scattering analysis is done to see the hydrodynamic diameter, and SEM or TEM, either SEM or TEM, these are done to estimate the electron microscopy diameter. So as we have already discussed that whenever you will put this nanoparticle in an aqueous medium, there will be formation of this electrical double layer. So that is why this is the hydrodynamic diameter, but this one is the electron microscopy diameter. So there will always be uh, it will always be like this, like the electron microscopic diameter will be smaller than the hydrodynamic diameter, and it also depends on the conditions in which it's working, because there would be formation of this electrical double layer, but in electron microscopic diameter which functions under vacuum, that too your sample needs to be dry. This is in dry state, but this one is done in aqueous state. So that's why. So DLS generally yields larger particle sizes than SEM, because DLS measures the hydrodynamic diameter, okay, which includes core, solvation shell, capping agents of particles dispersed in liquid. Whereas scanning electron microscopy measures the physical diameter of dry, often coated particles in vacuum. Now let us discuss what are some of the key reasons for this size variation. So hydrodynamic radius versus dry radius. Just now I discussed that this is done in aqueous medium, this is done in dry state, that too in vacuum. So measures particles in a hydrated state, including the solvent layer, which makes them appear larger. Same requires samples to be dried and under vacuum, leading to smaller naked core measurements. So aggregation and dispersion. DLS is a to even small highly sensitive to even small amount of aggregates, which can shift the entire distribution to larger sizes, whereas SEM allows for visualization of individual non-aggregated particles. Now, as we have already discussed, that DLS measures the intensity of scattered light proportional to diameter to the sixth power, making it biased towards larger particles. SEM provides a direct visual. So, see, like in order to understand the aggregation behavior, if your particle has colloidal stability or not, and what is happening to your particles when you are putting it in aqueous state, so for those conditions DLS is good. But if you want to visualize your particles clearly, then and in those conditions scanning electron microscopy is good. So as I have discussed earlier as well, that all of these techniques have have their share of pros and cons. So you have to validate your nanoparticles through all these techniques in order to conclusively come to a particular statement or conclusion for your nanoparticles. So SEM provides a direct visual number-based measurements. SEM samples are often coated with metal, which can alter the measured size. Obviously, we are doing sputter coating, so it can alter the size, while DLS measurements depends on the solvent and stability of the dispersion. Okay, the next technique that comes to us is Fourier transformed infrared spectroscopy. So by far we have already discussed. Okay, before coming to FTIR, let us first uh, kind of do a little, uh, I would say, discussion or a summary. So, by far, if any one of you have any kind of doubt or you want to ask anything related to the techniques that we have discussed so far, you can ask. Like, you can simply ask that if you have any doubt, or if you don't, if no one has the doubt, if no one wants to ask anything related to the video sessions that has been already been uploaded on NPTEL, we can like continue with the session also.
Yeah, hello.
Yes.
I had a doubt. See, in some papers, they give the zeta potential of the particles, right? So,
Right.
zeta potential is only of the particles. Now, in some papers, they have mentioned that zeta potential of the gel. Is that possible to get zeta potential of the gel?
See,
If you
by
are
yeah.
adding it in, say, polymeric gel like carbopol gel or, something like that, is it possible to measure that? Is it right?
Actually, as per me and as per my guide as well, what we discuss in this particular scenario, it's not theoretically correct to say this, because all these zeta potential measurements, this DLS measurements, they basically talk about. Okay. So they basically talk about the colloidal stability, and they basically talk for the particles. And when we're talking about gel-based things or the film that people are like kind of these days publishing, so we don't find it correct theoretically. But I think what they kind of trying to prove at that stage, what would be the correct thing is, suppose they are making some alginate-based gels or something like that. So if they are loading some particles in it for like for some nanoparticles in the gel suspension, they can do zeta potential for those particles. But quoting the zeta potential value for a thin film or for a gel for that matter, like doesn't make sense until unless it's some kind of, maybe they are proposing some kind of in situ gel, like when you are injecting like at usually at particular temperature, it's in liquid form. If it's in aqueous state, if it's like that, then maybe at some point they can convince. But if it is a like kind of solidified formed gel, it's not an in situ gel. Now in situ gel, what exactly is in situ gel is, at a particular temperature it remains liquid or in suspension, but when you inject it, like suppose if you inject it in a body, or at when it comes directly in contact at 37 degrees Celsius, it solidifies. If it's something like that, then maybe they're like they could convince. But still, like making doing zeta potential measurements or DLS measurements for thin film or gel doesn't make like kind of sense. Theoretically, it's not correct.
Okay, yeah. And one more thing, say, suppose like we are using chitosan, for
Hmm.
preparing the gel of nanoparticles. Means nanoparticles have been dispersed in a chitosan gel.
Okay.
Okay. So if we are checking the mucoadhesive nature of this chitosan,
Hmm.
okay, so is it right that we are again checking the zeta potential, and that mentioning that as the zeta potential is increasing, the mucoadhesive is increasing,
No,
because
I
the
don't
positive
think,
sign
like,
increases,
because see, what
something like
happens
that.
is, in order to actually experimentally prove this mucoadhesive nature of the thin film or gel, whatever people are making, so a lot of times I would say the instrumentation that is required to actually measure the mucoadhesiveness of a gel, like suppose if you are making it for some kind of patch for your oral thing or oral drug delivery or like that. So the kind of apparatus is not, kind of available, because what we were doing for one of the collab projects were we got the kind of the goat skin, like the epidermis skin, and we kind of used to stick the gel that we were making and then apply a particular force and see if it's coming down or not. And then in other case, when we were working for that one, there was one project of a colleague where they were making a kind of gel for some eye based application. So we got a goat eye. So there was a proper goat eye. Maybe I can show it in the next session also. So based on that, they were putting the gel on it and then seeing like if it's staying there or like that. So for all these applications, I think zeta potential doesn't make sense to me, because there are different set of experiments, actually different apparatus or different scientific procedures to actually check the mucoadhesiveness. But since a lot of things, a lot of these instruments are usually not available, so like just to prove a point, maybe they see कि, okay, we check that the zeta potential value is this, now it is changing. So maybe the point they are using to convince or to prove that okay, it's showing this kind of behavior is they compare like when they are using it solely, the potential is this. When they are modifying it, there is a change, and that change can, you know, be because of this mucoadhesive nature. So that again would be a kind of hypothetical kind of situation that we are proposing that, but it's not a scientifically sound way to, you know, um corroborate that it has mucoadhesive nature.
Yeah, right. Because it was, I saw in some papers and I was disagreeing that how come, zeta potential is being used to check the mucoadhesive nature. So I had a doubt, so I wanted to know.
No, that
And
doesn't not
you're
scientifically
right
sound.
that if you're using, say, goat nasal mucosa or buccal mucosa or even
Yes.
the eye, then you can prove that it is mucoadhesive. That's
Yeah.
right. Okay, fine. Thank you.
Okay, so let's continue with the session. Like we have three more techniques to discuss. Just a second. Okay, so the next one is Fourier transform infrared spectroscopy. So in nanoparticle characterization, this FTIR, Fourier transform infrared spectroscopy, is a primary tool for identifying chemical fingerprints at the molecular level. While techniques like TEM or SEM show the physical shape of a particle, FTIR reveals its chemical environment and surface chemistry as well. Now, why this FTIR is useful when we are talking about nanoparticles? Now, suppose in the previous sessions we were discussing like maybe we can decorate the nanoparticle with some antibodies or some other maybe some capping agents, or we are modifying it, we are putting a layer of protein, a particular kind of targeting protein or something, or RGD sequence or anything for that matter. Now we want to see, like we want to see if this particular coating or if this particular kind of decoration that we intended to do has happened or not. So in that case, we can do the FTIR of both the samples. Now another scenario could be, suppose we were talking about taking plant extract. Okay, we were talking about green synthesis, in which we were taking plant extract and then we were using it to synthesize nanoparticles, metallic nanoparticles. They were metal precursors, and then based on that, we were synthesizing nanoparticles. Now, in this case, also we can see, like we can record the FTIR spectra of raw plant extract, like the native plant extract, and after the nanoparticles are formed. Same for XRD as well. Now, this is one example. The other example is this nanoparticle thing in which we are decorating it with some peptides, some targeting peptides could be there. So, like that. Now, the basic instrumentation remains the same. There is a source, and then there is an interferometer, which is shown here, this interferometer. So, this is the infrared light source. Okay, and this is the sample. This is the beam splitter. The ray comes, it falls on the sample, and then this is a moving and stationary mirror which is used. So this is basically interferometer. It passes through the interferometer, falls on the sample, and then goes to the detector, which makes this interferogram. Now, what is the role of FTIR in nanoparticle characterization? So, surface functionalization and capping. So, FTIR is essential for confirming if a nanoparticle has been successfully coated with capping agents or stabilizers, okay, like polymers, proteins, or surfactants. Now, if you see here, this particular this black spectra that you are seeing, it is for the simple iron oxide particle, but this this red one is when this Fe3O4 nanoparticles have been coated with gold. So this is gold coated iron oxide nanoparticles. So when you are comparing the this FTIR spectra of both these two different nanoparticles, you would see the difference in the peak position, the peak broadening, and the intensity, and this transmittance intensity as well. So you can kind of compare, like as we know that in this FTIR spectra, different peaks correspond to different regions. So when we are studying at the molecular level, if we want to see the difference that has come, or if the coating has been done properly or not, we can, as a preliminary means, we can record this FTIR spectra. The second could be like just now I have discussed in green synthesis, researchers use FTIR to identify which functional group from plant extracts like hydroxyl, carbonyl, or amine groups were responsible for reducing metal ions and stabilizing the resulting nanoparticles. If you remember, I have discussed like the bioactives which are present in plant extract, it could be alkaloids or like that, which are used as a reducing agent for synthesis of like different metallic nanoparticles. Now, by analyzing the FTIR of this native plant extract and the nanomaterials that are formed, the FTIR spectra of these two, we can see that which functional groups in this plant extract have helped in reducing of these metal ions. Now the next one is bonding interaction. Shifts in peak position or intensities can indicate whether a ligand is chemi-absorbed or physi-absorbed to the nanoparticle surface. There would be changes in the peak position, there would be changes in the peak intensity as well. Now core identification for metal oxide nanoparticles, FTIR detects metal oxygen lattice vibrations typically found in the low frequency range. Now, this again is one example. So, this is the FTIR spectra of biosynthesized nanoparticles and plant extract. Now, carefully look at the spectra. If you look, this black line indicates the plant extract, right? So, you can see this black line indicates the plant extract. There are different, like this at the, it corresponds to the OH peak and all those things. Then C double bond O vibrations, PC vibrations, all those things. Now, when this particular plant extract has been used for synthesis of nanoparticles, you can see this green one is CS AG nanoparticles, this one, and this red one is CS gold nanoparticles. So they are different. There are changes in the peak intensity and some minute shift in the peak positions as well. Now the next technique is X-ray diffraction. So what happens in X-ray diffraction? So X-ray diffraction phenomena in which the atoms of a crystal, by virtue of their uniform spacing, cause an interference pattern of the waves present in an incident beam of X-rays. The atomic planes of the crystal act on the X-rays in the same manner as does a uniformly ruled diffraction grating on a beam of light. So as you can see, this is the atomic plane, okay? And the difference between these two atomic plane that we label is D. Now, this is the incident, we can say the incident X-ray that we are calling. A beam of X-rays contacts a crystal with an angle of incidence theta. This is the incident angle theta. It is reflected off the atoms of the crystal with the same angle theta. Okay, it is reflected off with the same angle theta. The X-rays reflect off atomic planes in the crystal that are a distance d apart. The X-rays reflecting off two different planes must interfere constructively to form an interference pattern. Now, if these are the two different atomic planes and these two are the reflected X-rays, these two X-rays must interfere constructively in order to form a signal. The X-rays would interfere destructively and there would be no pattern formed. So to interfere constructively, the difference in path length, okay, the difference in path length must between path length between the beams reflecting of two atomic planes must be a whole number, that is n of wavelengths, that is lambda or n lambda. This leads to the Bragg's law. So see, what we need to study is this is some the core physics that we studied in class 11th and 12th, the X-ray diffraction, Bragg's law. So I would not dwell too deep into it, but I would just revisit the concept once, and then I will be directly coming to how this XRD and XRD diffraction this thing is used to study the used as a nanoparticle characterization methodology. So by observing the interference pattern, the internal structure of the crystal can be reduced. Now we all know about the constructive and destructive interference, right? So XRD allows one to ascertain the molecular structure of a crystalline material by diffracting X-rays through the sample. Okay, so whenever we have a crystalline material and you want to ascertain, like suppose you have a plant extract, right? And you have a plant extract and you intend to make metallic nanoparticles, suppose copper nanoparticles, silver nanoparticles, or gold nanoparticles, right? Now you have plant extract, you can record the XRD of this one, and then you can record the XRD of these nanoparticles in order to actually understand if you have achieved this or not. So an XRD analyzer obtains interference patterns reflecting lattice structures by varying the angle of incidence of the X-ray beam. Okay, XRD finds the geometry or shape of a molecule using X-rays. It's based on elastic scattering. I think this will get more clear when I'll move to the subsequent slide where there is the instrumentation thing. So I am just reading it because this is the core concept. So the X-rays get diffracted by a crystal because the wavelength of X-rays is similar to the interatomic spacing in the crystal. So usually what we do is we we keep the angle 2 to 90 degrees. So in all, like it will range from 2 to 90 degree to 3, and it will move like that. And then at some point this thing will match the interatomic spacing of the crystal. So X-ray diffraction is based on constructive interference of monochromatic X-rays and crystalline sample. These X-rays are generated by a cathode ray tube filtered to produce monochromatic radiation, collimated to concentrate and directed towards the sample. We know that whenever there is constructive interference, we get a strong diffracted beam is strong, but when it is out of phase, that is destructive interference, diffracted beam is weak. Now this is the instrumentation. Okay, so we see this is the X-ray tube and this is the detector, and this kind of moves. Okay, this kind of moves. Here you put your samples, and whatever whenever X-ray is shooted on the sample, it kind of moves like this, and it will keep uh, falling on it. So when a crystal is bombarded with X-rays of a fixed wavelength and at certain incident angles, intense reflected X-rays are produced when the wavelengths of the scattered X-rays interfere constructively. In order for the waves to interfere constructively, the difference in the travel path must be equal to integer. ये हमने पढ़ा, that is regulated by the Bragg's law. So by measuring the angle 2 theta of each diffraction peak, you can calculate d for the corresponding crystals. These d spacing are fingerprints of a metal's crystal. Now this particular line is important. So whatever d spacings you get are considered as fingerprints of a material's crystal structure, and these fingerprints will be characteristic to that particular material only. So you can see this is diffraction radius, focal circle, like how this X-ray tube moves and illuminates the sample. This is the X-ray tube, and then detector, the rating detector, and receiving slit and scattering slit. So let us understand the XRD spectra. So this one has been done for gold nanoparticles. Okay. So whatever you see, this peak, then this peak, AUT20. So what does these peaks indicate? This is the XRD pattern for gold nanoparticles that it form. So in a X-ray diffraction pattern, labels like 220, 311, 400, like for this one, this is for iron nanoparticle. This is for iron nanoparticle. Okay. Uh, these indicate the Miller indices HKL of the crystallographic planes responsible for each diffraction peak. So always remember these peaks, it represents the Miller indices. So each labeled peak corresponds to diffraction from those planes. So whenever there was diffraction, each peak represents diffraction from a particular plane as per Bragg's law, which says n lambda, this integer, and this wavelength 2d HKL sine theta, where d HKL spacing between these planes, which represents the Miller indices. Theta diffraction angle, X-ray wavelength, and different HKL planes have different interplanar spacings. We have seen that it will have different interplanar spacing, and based on that, it they produce peaks at different 2 theta values. So, in suppose you have a plant, you are making copper nanoparticles from a noble plant extract. Just suppose that you are making nanoparticles from a novel plant extract, like that plant extract has not been earlier reported for making that kind of nanoparticles. That is something novel. Now, in order to, because in literature we have enough data, like whenever the copper nanoparticles are formed, whenever this gold nanoparticles are formed, there would be certain specific this Miller indices. We know these values. Now, when we are synthesizing, suppose copper nanoparticles from a novel plant extract, and we get spectra somewhat similar to this, like this, and if then we what we do is we match it with what is available in the literature, these Miller indices and these spectral patterns, at what positions it's coming, that this 2 theta values we see, we look for these 2 theta values, and then based on that, by comparing it with already reported, we say that okay, now we were proposing that we are making copper nanoparticles, and based on what is available in the literature, we can conclusively or we can experimentally say that we have synthesized the copper, gold, or iron nanoparticles. Okay, so now we'll do some questions. Uh, I want all of you, to kind of attempt, because I have put very basic questions, because the difficult ones or a little up, we'll discuss those questions once we are done with all those sessions. So since we have only discussed the basics of everything, so all these questions are very basic, and I hope you can, like, you all can at least try attempting. You can write the answers in chat box also, and once all three questions have been answered, we can, like, kind of discuss the answers as well. The first question reads, UV-Vis spectroscopy is mainly used to determine. We have seen that we record absorption spectra of the nanoparticle suspension that we have. So what exactly it determines? Does it determine the particle shape, the crystal structure, optical properties in SPR peak, or surface roughness? So obviously, when we're talking about the absorption spectra, it doesn't show us the particle shape, it doesn't tell the crystal structure, not the roughness, because whatever SPR peaks, right, the correct answer is optical properties and SPR peak. We have seen, like, for gold nanorods also, we have seen two different LSPR bands. So it shows the optical properties, because different nanoparticles would have different, like for gold nanomaterials also, different gold nanomaterials have different optical properties based on what size, shape they are being formed. The next question is, the appearance of surface plasmon resonance peak confirms. So does it confirm amorphous structure, nanoparticle formation, bulk material formation, or porosity? Right. Obviously, the nanoparticle formation, especially metal nanoparticles, because we have discussed for gold as well, that when we're talking about gold, if we are getting a peak at somewhere around 520 or like that, so it indicates spherical gold nanoparticles of 20 nanometer in size. So this is just one example. For different, like for gold nanorods, there would be two peaks. So this surface plasmon resonance peak confirms nanoparticle formation. The third question is, a red shift in UV-Vis peak generally indicates. Now we have studied this as well. We have seen under what circumstances this red shift is observed. So okay, so let's discuss. The correct option would be increase in particle size only, because suppose whenever there is this case of aggregation, whenever there is some sort of aggregation happening, or because of aggregation there is increase in particle size, there'll always be a redshift. Okay, we'll always observe a redshift. We have also seen it in the initial slide where we were discussing about the theory of this UV-Vis spectrophotometer functioning in principle. Just a second. I just want to see if the annotation that I'm making it's visible or not. Okay, yes, fine. Yeah, this one. It was not coming. So as you can see, if you're getting a peak in the visible region, right? If whenever there is increase in particle size, okay, whenever there is increase in particle size, some kind of structure or some kind of aggregation that is happening, there will always be a shift towards the NIR region that we call as red shifted absorption, yeah, super large red shifted absorption. So always remember this concept. Now try attempting these questions. We'll go one by one. So the first question reads: SEM is mainly used to study. First is internal atomic arrangement, surface morphology, chemical bonding, and optical absorption. Obviously, this would not be the case. No, we don't study because we are simply visualizing what we have made. So in this case, it's a very straight answer, like we are observing for surface morphology. Right, correct, good. So the next is SEM images are formed using. We have seen that scanning electron microscopy is a kind of electron microscopy, right? So if we are talking about electron microscopy, the answer is but obvious that it would be electron beam. So these are actually very basic questions. So the purpose of putting it here is like we kind of revisit the topics that we have discussed just now at a very basic level. So as to just you know do the simple by doing the simple questions. So SEM provides information about particle size and shape, band gap, zeta potential, crystal defects at atomic level. Right. Correct answer. Nice. So the answer would be A only, particle size and shape. Now the third question is for transmission electron microscopy. So transmission electron microscopy provides information about. C. So obviously the C and D would cancel out. Yeah, right. C and D would cancel out. Now, TEM does not only give information about surface roughness, it gives internal structure. If you remember, we saw that pollen grain image where we saw, yeah, right, good. So in the pollen grain image in which we could see some of the internal features as well as the surface roughness as well. So TEM provides both internal structure as well as lattice fringes. So TEM has higher resolution than, if you remember, we have discussed the resolution and the detection limits of all these three techniques. So obviously, if we're talking about transmission electron microscopy, this would not be the case, not be the case. So the correct answer would obviously be scanning electron microscopy. So in transmission electron microscopy, electrons, do they reflect from surface, pass through thin sample, are absorbed by solvent, produce fluorescence? Right. So obviously, this one we have very clearly discussed. We have very clearly seen in that one image where we saw how the optical path of the electron, like sorry, I would not say the optical path correctly because the path of the electron beam, how they are passing from the source and through the samples. And in TEM, we saw that it passes through the sample and it's the transmitted forward electrons that are used to reconstruct the TEM images, and in case of SEM, there was formation of 3D image with the help of backscattered and secondary electrons. So the correct answer would be pass through thin sample. It passes like this. If this is the sample, and then the image is created here. So obviously the correct answer would be this one. Now, some more questions before we end this session. Okay, let's write answer one by one. Like for the first one, DLS works based on, this is a very simple thing in the slide also I mentioned. Right, this is a very, like very basic one we have seen. Like this is your sample cell, the laser would fall on it, there would be scattering, there would be Brownian motion between the particles, and this laser would be scattered. So, right? So, atomic force microscopy also we have seen. So, AFM can measure. Try answering this one. So, now the options are like simply can be eliminated out in one go. Obviously, all these three won't fit in. So, it talks about the 3D surface topography. And one important feature that we highlighted in atomic force microscopy was like how it was better than SEM and TEM, because SEM, how it's better than SEM because it doesn't require, it gives 3D, I mean 3D surface, it gives information about 3D surface topography only, but it doesn't require any additional coating. Like in case of SEM, what we were doing, we were kind of sputter coating the sample. We were sputter coating the sample with some conducting material like gold, copper, like that. But in case of AFM, we don't need that kind of coating. So in this sense, it's better. So just kind of revising that point. So yes, the correct answer is A. The next question is AFM can operate in. So we have also studied this one important feature of atomic force microscopy, like how is it better, because electron microscopy works only in vacuum, but atomic force right, atomic force microscopy works in all three environment: air, vacuum, and liquid. So if you look at the questions, you'll like kind of feel that these are very basic questions, simple, but actually these are very basic questions that you must know. Okay, so from as a scholar point of view, or as a student point of view, we have nanoparticles. Okay, I'll simply characterize it. These are the different techniques. I'll do it, I'll get the data. But it's very important at this stage that you know the exact principle that is being followed in that methodology. That what is the principle, what is the instrumentation, like the very fine differences that we saw between the instrumentation setup for the absorption spectrophotometer and in the fluorimeter, the reference cuvettes, from where what is the optical path of light. Like in case of absorption, it was a straight, then 180-degree. Then in case of fluorimeter, there was a 90-degree deflection that we saw. So all these are very basic, very, I would say very small, subtle things, but all of us should know this like basic things. So a sharp XRD peak indicates, what does it indicate? I think a lot of people have already answered it and answered it correctly. So yes, it indicates good crystallinity. Now a broad XRD peak usually indicates, because if you remember, we have seen in some of the examples as well, like it nanoparticles or small crystallite size, it indicates. So these are some of the basic questions. So I have uploaded the lecture, I mean this particular PPT, in the drive link also, so you can access it there, and the session would also be uploaded uh, on YouTube as well. So if anyone has any doubts, you can ask, or we can like, end the session for today. Okay, so like you can also like go through all these topics, and it's not like whatever questions you want to ask, it should be limited to what course content we are dealing with. If you have like, because I am also working in nanotech only, So you can ask anything related to, like, if you're talking about nanoparticles, nanotechnology, and all those things. I I'll try, like, if I have worked on it, if I know about it, I'll definitely answer. So it's not like you have to restrict your questions to these particular topics only that we're talking about. We can discuss about other topics as well. Maybe at some point, maybe at that point, I might not know, but I can definitely come up with, you know, answer in the next session. But if I know at that point only, I'll try answering that. So it was nice having you all, and thank you for promptly answering, for interacting, for asking questions. Thank you for the session. Thank you.
Anusha, one question.
Sure.
Actually, one of my friend, had joined this course, but somehow she is not receiving any of the emails and all. Can anything be done for her? Like, she at that point, like I told her, you joined, and she had joined,
Okay.
but she didn't receive any emails. Is it possible
Actually,
for you to?
I raised this concern.
Mm-hmm.
So I think she can. I'll just write the email ID which they asked me to give the students who are facing this problem. I'll
Uh,
just write in the chat box. So I think she can email at this support@nptl.itm, that is
okay.
itmadras.ac.in. So
Okay.
citing her concern, because I've already raised this issue to the support team, and they said either she would have got email and it could be in the spam folder, but if
Uh-huh.
by any reason she's not able to receive the mails, she can mail it at this email ID.
Okay. Fine. Yeah. Thank you so much.
Thank you. Thank you
Yeah.
all.
Yeah. Bye.